I'm going to start by using the product rule. There's all my ingredients, and the product rule is the one with a plus. We start here with the u, and we go u dv by dx plus v du by dx. But I'm going to write it down for the examiner because they do like to see it, not quotient rule. U dv by dx plus v du by dx. And this is really important for picking up all the marks. Most students don't like doing it. They hop straight from here to here, and so would I if I was just doing maths just for fun or homework or something. But in an exam, make sure your ingredients are really, really clear and that you write down the formula. Now at this stage, notice that I have x squared minus 1 to the 5, and I want to pull out x squared minus 1 to the 4. So this is the same as x squared minus 1 to the 4, which is what I'm going to pull out, multiplied by another x squared minus 1. Okay, g of x is a function to be determined. The function to be determined is 22x squared minus 2. Now, it doesn't actually say giving g of x in its simplest form, but if it did, we would need to pull out that common factor of 2, and that would be g of x in its simplest form. This is dy by dx here. And we need that to be greater than or equal to 0. Now, anything squared is always greater than or equal to 0, always. So if this product is greater than or equal to 0, then this bit here must be greater than or equal to 0. So what we actually need to solve is that this thing here, 22x squared minus 2, is greater than or equal to 0. Now, I've deliberately done this wrong because I want to show you what happened when students did this in the real paper. We got several answers, most of which look like that, and this is very wrong. And some of them even had equals here. Some of them were missing the plus minus, as you can imagine, but this is not how we solve a quadratic inequality. The way to solve a quadratic inequality is to imagine its graph, or even better, draw its graph. So this is 11x squared minus 1, to put the roots on the graph, which are plus or minus 1 over root 11. And then to think about whether we want the inside of the roots where the graph is negative or outside the roots where the graph is positive. So this says that we want our graph to be above the x-axis, greater than or equal to 0. So we want the bits above. We do not want this bit here below the x-axis. So what we want, the x is to the left or equal to minus 1 over root 11, or the x is to the right or equal to 1 over root 11. Don't write and here. If you write and, you're going to lose a mark because x can't be here and as well here. It just can't be. It's either to the left of this one or to the right of that one. It can't be both to the left and to the right at the same time. So this is really important that you use a comma or the word or. You cannot write the word and. I'm using the chain rule here because I've got a function inside a function. So I'm going to multiply by the derivative of sec 2y. Actually, there's another chain because 2y is inside sec. So I'm going to get the derivative of sec 2y multiplied by the derivative of 2y with respect to y. Okay, we're nearly there. It says we need to give our answer as a function of x, not as a function of y, and also I need dy by dx, not dx by dy. So I'm going to turn it upside down, and I'm also going to work out how I can write this using x's. So there's a little hexagon thing that you can use for your Pythagorean identities, which is quite nice. We have tan, sine, cos, and then opposite put the reciprocal. Then sine squared plus cos squared is 1. 1 plus cot squared is cosec squared. Tan squared plus 1 is sec squared. And we're looking for some way to connect tan with sec because we've currently got a tan 2y in our derivative, and what we'd like is something to do with sec 2y. Ideally, if I do e to both sides of this, e to the x is sec 2y. So if I can create something here that instead of tan 2y says sec 2y, then I can just replace it with e to the x and I'll have a function of x. So from this little hexagon here, I can see that the connection I want is tan squared plus 1 is sec squared. Tan squared of the angle plus 1 is sec squared of the angle. So tan 2y is going to be this thing here, which is e to the x squared, minus the 1, and then square rooted. And that can be written as the square root of e to the 2x minus 1. So, having done that, I can go, this is kind of an aside, I can go back to my 2 tan 2y, I can turn it upside down, and instead of writing tan 2y, I'm going to write the square root of e to the 2x minus 1. And I found dy by dx, and it's a function of x, and that's in its simplest form. There's nothing obvious that I can factorise out or anything like that here.